Kannst du gerade noch warten?
No, maybe.
Should we get questions from those people first?
Well, I have a funny question about online banking. You know, most online banks, or banks in general, which have an online service in Holland here, use some sort of cryptographic device, which you have to insert your banking pass in.
Right.
And they have some sort of hardware crypto loop, which requires a challenge from the website and a PIN key, and that gives a response, and that should authenticate you.
Yes.
How safe is that?
Well,
That's really the question.
They're hackable, but probably not hackable to a degree that would concern you as a customer of a bank for online banking. There's always a way of extracting all information from a card to make a clone of the card. In a process, of course, you destroy the card. So if you give your banking card to somebody and allow them to hack away with it for days, they'll have a clone of it. In the meantime, of course, they could already have used the original card you gave them to steal money from your bank. In many applications, breaking doesn't mean compromise.
I didn't mean the banking card. I meant the cryptographic device which you get from the bank.
I mean like an RSA hash chain secure ID?
The label doesn't say what cryptographic system is used.
Is it the thing that every minute shows a different number? It's called the secure ID. It's cryptographically sound as long as the information stays in it. Again, if you give somebody a couple of days to hack away at it, they can create a clone. In the meantime, though, they could already have used the one you gave them to hack into whatever you're trying to protect. So yes, if you lose physical control of these devices and somebody is determined enough, as in $100,000 to hack it, then they'll do it.
But this device is generic. It is not bound to a person, you know. You have to insert your banking card in it. That should physically identify you. So these devices themselves, these cryptographic devices themselves are generic. You can get them, well, for like 20 euros from your bank.
Well, there will be a secret involved at some stage, and it will be extractable if you give somebody a couple of days' time in a lab and allow them to hack your card, in which case they could have already stolen your money.
So they're not safe.
So yes, they're hackable, but not of concern. Banks usually use standard cryptography, and you're only concerned with protecting the secret keys. You're not so much worried about the secret keys leaking through bad cryptography.
What he meant was just a bogus reader that reads the smart card, and you can enter your key in the reader, and then it eventually reads the smart card. That's the whole idea. Yeah. Yeah. Yeah, but you can easily reverse engineer it. Yeah.
Any other questions?
I have a question about the pattern recognition algorithms. When you're recognizing a gate on a chip, can you take it back to the VLSI program that generated it and figure which program the engineer used to design that chip?
Well, we can't figure out what was used to design the chip. No. Well, we can recognize a library. Most often what happens is the person designing the chip doesn't even know what the gate looks like. So in his tool chain, there is no such thing as a fully specified gate. It will draw a block saying, put a 2 NAND here. It will send it off to the foundry in the standard format, and only in the foundry, these black boxes will be filled, right? Yes. We can, of course, see when it's using the same library, the same foundry, right? Those will use the same patterns.
Sure. I guess the thought might be, if it was known that a particular library had a vulnerable random number generator that gets implemented down into logic, you could...
Well, these logic blocks are completely verified. There's no such thing as a broken inverter, right? And a random number generator is always composed of different parts on the gate level, right? Of course, there might be some IP block, a broken random number generator that different manufacturers use. That's not the level of pattern that we recognize, though. We could. If we looked at very similar chips and only wanted to recognize the difference, we would probably go down that road, but we haven't yet. Thanks for the question.
So how usable is it? Because I want to reverse engineer FPGAs, old ones, and the problem is that we need some automated tool because nobody would like to point and click and look for metal layers. So I want to have a net list. So I can make the logic from the FPGA.
Well, I can't see why an FPGA is any different from any other chip. So you can already use the existing tools, or you can wait a couple of months, have it more automated. An FPGA is huge, but highly, highly structured. An FPGA has the same structure thousands or millions of times. So you reverse engineer it only once. Tiny piece of your chip, you reverse engineer, you know how the rest of it is working on a cell level. So it's probably a good target for this. The most recent FPGAs, though, you won't be able to optically take pictures of.
We wanted to take old Xilinx FPGAs because the patents are run out, and so it's possible to make something interesting with them. And so there was a famous FPGA, it's called the 6300. It was partly reconfigurable, and Xilinx doesn't produce them anymore. And they're very sexy FPGAs, and so we want to make them our own.
Well, being able to reverse engineer it doesn't yet mean that you can reproduce it, right? So probably you're out of luck trying to assemble anything beyond a very simple circuit yourself. I've been producing chips at my university. It's something upward of $50,000 for a single run. And you get tiny chips for it only. It's very costly. A chip fab is a couple $1 billion right now. So you need to know somebody who owns one pretty much.
If you take an old process, maybe 0.35 nanometers or something, micrometers. So old processes, for example, that were used for 10 years ago or something.
Well, they're not being used anymore. So yeah, we can chat later. Yeah.
You won't find the factory doing this. Okay.
Those factories just don't exist anymore, right? Sorry to disappoint.
Are you seeing attempts by the chip makers to prevent this kind of attack, such as obfuscation or something?
Of course, yeah. There's a couple of ways they try to make reverse engineering much harder. They only look at manual reverse engineering, though. People that look for exactly the instruction ledgers I've been talking about, that will put those in as random of an order as possible. With an automated approach like this, if all you're interested in is find out what function produces a certain output, it doesn't really matter in what order the gates are or how weirdly they're connected to each other, whether there's fill logic that doesn't contribute anything. The tools will just find the core that produces the functionality and will print it out in a nice circuit diagram. So all the obfuscation they put in tries to defeat human intuition, as in these should be in order, they're not, so I give up. The tools don't really have a concept of intuition, so they don't care.
They're adding a cover layer on top of it to prevent making pictures directly to the chip, but it's just another layer, so you can polish it off and make a picture of the layer below it. So it's just one step more.
Yeah, but as I was saying, common criteria is considering putting more reverse engineering protection requirements into the EAL certificates. So it'll be interesting to see what they think prevents what we are doing.
I missed most of your talk, but how many metal layers can you actually do? And if you polish them off, how do you do the coplanarity of the layers? So you're not like polishing off half of the next layer and then you're not getting images.
So the chip with the most numbers of layers was the MIFARE chip. It had 6 layers, but you are not limited to any amount of layer. So